Good evening, everyone. Welcome to the 8th problem solving session of NPTEL GATE series. Today, we'll be looking at the topic of structural analysis. I'm Naresh, a research scholar in the Department of Civil Engineering, IAS. You can access the presentations used for this session from the Google Groups or the NPTEL portal itself. Wherever you find all the recordings in the same folder, drive folder, you can find the presentations as well. So let us quickly get started. In today's session, we'll be focusing on mainly on the analysis of statically indeterminate beams by two methods. One class of methods is known as the force methods of analysis, wherein the forces are treated as unknowns. And the other class of methods called the displacement method of analysis, where the primary unknowns are displacements and slopes. The reference for whatever I'm covering today is the book by R.C. Hibbler, Structural Analysis, the latest version in SI units. We'll also be solving a few gate problems for practice. So let's get started. Before we get into today's problems, let me quickly go through an overview of structural analysis. So basically, methods of analyzing a structure can be a statically determinate structure can be divided into those methods that are meant for beams and those that are meant for trusses. So for beams and frames, the difference is that they resist bending moments and shear forces, whereas in truss, all the members are axial force members. So for truss, you basically have the method of joints and method of sections, but we are not going to focus on trusses in this session. So let us look at the methods available for analyzing beams. If it is a statically determinate beam, in order to find the deflections and the slopes at various points in the beam, we can use either the Macaulay's double integration method, where this is the double integration method. This is the moment curvature relationship. So the second derivative of deflection with respect to the axial coordinate is the curvature of the beam at a point, and that is related to the moment, the bending moment of that section, as m by ei is equal to d square v by dx square. So this is a second order linear ordinary differential equation. Determining the bending moment in a statically determinate beam is very easy. How do we do it? So that you can obtain just by enforcing the equations of equilibrium. So for beams, you take a section at an arbitrary coordinate x and then take one of the two parts. So let me write it down. For a beam, determining the bending moment as a function of x, we take a section at an arbitrary coordinate x and consider the equilibrium of forces and moments of one of the two parts. So the section will expose a bending moment, a shear force, and an axial force. These are called N, V, and N. And these three unknowns can be solved for by enforcing the three equations of equilibrium, which is sigma fx equal to 0, sigma fy equal to 0, and the sum of all moments about the z direction is equal to 0 for this for this part of the structure. So this will we can determine the bending moments and the shear force as a function of the coordinate on the beam. And once that is determined, then getting the deflection is a straightforward integration. So this just have to be integrated to get the deflections. And this integration would result in two arbitrary constants, two constants of integration, and those are to be determined by enforcing the boundary conditions. Now, we also have the other methods such as the moment area theorems and the conjugate beam method, which are essentially based on the Macaulay's double integration method, but these are more graphical. The moment area theorem is more graphical, whereas this is more algebraic. This is algebraic. I wouldn't get into the details of all these due to time constraints. So as I will be sharing the presentation, you can review it. Then another useful principle, which we have also looked at in the plastic analysis of structures and several other sessions of this series is the principle of virtual work. So the principle of virtual work states that if a body is in static equilibrium, then the virtual work done by the system of forces on any kinematically admissible virtual displacement field should be equal to 0. So if a system of forces Fy, so forces in general also refer to moments. So if a system of forces and moments and support reactions on a body is in static equilibrium, then it is a necessary and a sufficient condition that the virtual work done, the work done when the forces act on any arbitrary kinematically admissible virtual displacement, the net work done should be equal to 0. There is a proof for this, which we are not getting to the details. So this basically translates to the sum of all external forces multiplied by, so these, the component of the displacement of those points along the direction of the force should be equal to the sum of all internal forces. So the internal force can be a bending moment, it can be an axial force or a shear force. So the sum of all internal forces summed over by in both cases multiplied by the internal virtual displacements. For a continuous structure such as beams and frames, which are commonly encountered, this integral becomes this summation becomes an integral. So this is also well known. We'll be solving problems, so don't worry about it. And an extension of the virtual work method is the unit load method, where if you want to, wherever we want to determine the displacement, you apply a virtual unit load. Therefore, the left-hand side becomes just the component of displacement we wish to compute. And coming to the force methods of analysis, we have something called the Kleprov's theorem of three moments. But it is not really advisable to use this in an exam like GATE, because you will have to remember the entire thing, and a sign mistake or a problem with the sign convention could give an entirely wrong answer. But it is good to know the method. It's a classical method, so it is good to know this method, and you can use it for practice for this field. But it is better advisable to use the method of consistent deformation. So the method of consistent deformation is very clear. Given any structure, you determine the degree of static indeterminacy, because that will be the number of unknowns which you will be solving for. So if the static indeterminacy is ns, you need to arrive at least at ns geometric compatibility equations. So then, once you have determined the static indeterminacy, identify a number of redundant forces. How many redundant forces? The number of redundant forces should be equal to the degree of static indeterminacy. Remove the redundant forces. It can be a support or an internal force, and release the corresponding degrees of freedom, so that the resulting structure is statically determinate and also stable. So this is called the primary structure. So now, using the principle of superposition, as it is a linear elastic structure, we can use the principle of superposition. So whatever system of forces and reactions we have on the structure, we can decompose it as the primary structure subjected to the applied forces, plus the primary structure subjected to the redundant one, plus the primary structure subjected to the other redundants. So superposition of all these should respect the geometric constraints. So this will give us, so if there are ns unnecessary geometrical constraints, they will correspond to ns redundant forces. Therefore, by enforcing the ns number of geometrical compatibility constraints, you get a system of ns cross ns equations, where the primary unknowns are forces, and on the right hand side we have some displacements. So this matrix is called the flexibility matrix. These are the unknown forces, and this is the applied or specified displacements. So this can be solved for the unknown forces. The problem with this method is that it comes up with a full matrix. So a force applied at any point in the structure will cause displacement throughout the structure. So this matrix is usually very dense. It is fully populated. Not only that, this requires certain uh, this requires establishing equilibrium. So the primary structure, redundant structure, all of them have to be individually in equilibrium. Only then we can compute the force displacements due to the applied forces on the redundant forces. So the evaluating the flexibility coefficients involves solving the equilibrium equations for every structure, and that cannot be computerized easily. Therefore, this method is not typically used in the analysis of real life structures. Very large scale structures, the degree of static indeterminacy is very high. Therefore, this method is cumbersome. So that is why displacement methods of analysis were developed. So we have the slope deflection equations, which is written for one span of a beam. Or it can be a continuous beam. Its static indeterminacy can be anything. But what is important for enforcing the displacement methods of analysis is the degree of kinematic indeterminacy. Why is that? Because the unknown displacements are the primary unknowns. Therefore, identify the degrees of freedom or the which is also known as the kinematic variables of the problem, and then use these two equations. So the derivation of these two equations is very straightforward. You can use either the conjugate beam method or another force method to derive these. So if you have a span AB, in the slope deflection equations, all the clockwise moments are taken as positive. So MAB is the moment on the beam in the clockwise direction at the point A, and the moment on the span AB at the point B in the clockwise direction is MBA. So, all clockwise moments and clockwise rotations are taken as positive, and the displacements, the sway degrees of freedom. So the kinematically is something like this. So there can be a rotation here. This is a positive sense. This is theta AB, or rather theta A. Again, this is a clockwise rotation. This is theta B, and the entire beam has rotated. The chord of the beam has rotated by. You see, the chord of the beam has rotated by a value. If the relative vertical displacement is delta, this would have rotated by a value of tan inverse of delta by L. And in the small deformation range, you can take it approximately as delta by L. So delta by L, theta A, theta B, all are positive when it makes a clockwise rotation. So the end moments in a span are related to their end rotations and the chord rotation of the beam by this formula. This is the famous slope deflection equation. So you have 4a by L theta A plus 2a by L theta B minus 6a by L square delta, plus if the beam is subjected to certain applied forces, span loading, that will also have an effect. So this basically arises by the superposition principle. Initially, we assume that the ends are fixed and we see what is the moment. Then we allow a rotation of theta A, remove the loads, and we see what is the moment. That will be 4a by L theta A. Then you arrest all the ends and you rotate the end B by theta B. That will result in a moment of 2a by L theta B at the point A. And if the entire B has just a vertical relative displacement by delta without any end rotation, that would result in a counterclockwise moment at the point A of magnitude 6a by L square delta. So this is basically how the slope deflection equations are derived. Once we get the expressions for the span end moments, the next step is to enforce joint equilibrium. So if you have two adjacent spans, we can write the slope deflection equations independently for this span and then independently for this span. Let's call it A, B, C. If there are no external moments acting at this point B, then the condition of equilibrium is that the sum of all moments at the point B should be equal to 0. So what are the moments acting at B? It will be MEA and MBC. So this should be equal to 0 if there is no external moment, or it should be equal to the external negative of the external moment if there is an external. So that's all. Similarly, if it is a sway frame, there's somehow you just have to determine all the shear forces in terms of the bending moments and then enforce the condition that the shear force the equilibrium of forces is satisfied. The resulting system of equations is solved for the unknowns theta A, theta B, and delta. So once we have solved for them, we have all the we have the solution. Once we get theta A, theta B, and delta, we can determine the moments MAB is given by this expression, and we have the complete solution for the problem. So this is a quick, and we also have the moment distribution method. Again, it's an iterative method. So typically, this may not be useful. But it is very useful for computer implementation. So in Gate, it's a bit difficult to draw the table and determine the moments. But you may have some small question dealing with the distribution factor, carryover factor, and all. But those are things to do with just one joint or one point. So, but you may not be you may not have to solve the full structural analysis problem using the moment distribution method, as it is slightly lengthy. It is iterative. So you can also go through this. I'll be sharing the slides. Then, yeah, direct stiffness, I don't think it's important at this stage. So let's get into today's session. Let us look at this problem, which was asked in GATE 2023 civil engineering paper of set 2. We are given a square frame, and then it is mentioned that all 4 members have the same length and same flexural rigidity. So it is given that let us take the flexural rigidity of each member as EI and the length as probably 2L, because, and let us take the origin at this point. Let us take this as the origin. So this is our x-axis and this is our y-axis. All the joints A, B, C, and D are rigid joints. The midpoints of AB, BC, CD, AD are denoted by EF, G, and HEF, GH. So this is a multiple select type question. There may be more than one correct option, or there can also be just one correct option. So we are asked to find, we are given a set of 4 statements. We need to find which of the following are true. There can be just one correct statement, or there can be many such statements. So let us look at the structure first of all. Before we get into the options, we need to try to exploit as much as we can from the structure. So this is how we have. This is what we have. Here's a line drawing. This is the x-axis, y-axis. Yes, this is A, B, C, and D. It is subjected to a pair of equal and opposite forces that are also collinear. Let us call the force as E. And the length we have taken as L and the flexural rigidity as EI. First of all, you see there is one information here. The frame is in unstable equilibrium under the shown forces. So why do you think it is in an unstable equilibrium? In my last session, I have looked at the aspects of stability of structures. And what did we say? An equilibrium configuration essentially means all the forces and moments are balanced. But how stable it is? The question how stable an equilibrium, the question involving the stability of equilibrium has to do with perturbations, small perturbations about the equilibrium configuration. So suppose we have a column subjected to equal and opposite forces, and you slightly give a slight deformation to the column. Is it stable enough? Would it deform uncontrollably? So when we slightly perturb a structure from equilibrium, the forces can no longer be in equilibrium. So there will be an acceleration. There will be a resulting acceleration. If that acceleration tends to bring the structure back to our equilibrium position, then that equilibrium position is called stable. That equilibrium configuration is stable. And if the acceleration tends to take the structure far away from the current equilibrium configuration, then that equilibrium configuration is unstable. So the classic example we saw was the ball inside a ball kept over a ball. So this is a stable equilibrium configuration because if you disturb the ball slightly, there will be a resulting acceleration, which is g sine theta or whatever, and that will try to bring the ball back to the original position. But here, if you disturb it slightly, the ball will just run away. In this case, why do we say it is an unstable equilibrium? It is because suppose you you create a small moment about the suppose you perturb the structure with a small rotation. So now everything, the forces are collinear, equal and opposite. Therefore, it is a two-force member and it is in equilibrium. But suppose I rotate the structure by some very small angle. This is an exaggerated view. But if we rotate it by a very small angle, say delta theta, then these two forces will be off slightly. But this has undergone a rigid rotation. And what does that mean? The rigid body, this rigid body, it doesn't have any support. So it is just going to rotate freely. This has got this rotation is in the clockwise direction. And the resulting moment, the resulting couple due to the small distance is also in the clockwise direction. So the acceleration, the angular acceleration due to the couple tends to rotate the structure in the direction of the perturbation. So it is unstable. That is fine. Now, what else is that we know? We know that all the four members are equal in are identical. They have the same length and same EI. So they're identical, which means that if you take a mirror image of this, if you take a mirror image of this about the y-axis, you will see exactly the same. And similarly, if you take a mirror image of the structure about the x-axis, you will see exactly the same. Because both, so this is something to do with the symmetry. So the structure, the material properties, and the loading and the boundary conditions. If they are all symmetric, so these are all symmetric about a plane, then the displacements. So these are all known things about the structure. So if they are all symmetric about, say, in this case, the x-axis and the y-axis, then the displacements, bending moments, shear force, all internal forces, reactions, etc., etc. All the unknowns, they are also symmetric. Right? So that is what it means. In this case, we have statements that relate to the shear forces, uh, the horizontal displacements, vertical displacements, and the slopes. So let us look at each one of them. Let us look at each one of them. So as I said, the first thing to see is the displacements are symmetric on both sides. So if the deformed shape is something like this, the geometry and the structure is symmetric about the y-axis. So what does this mean? If you take a point here at a distance x, and you take another point at a distance y, sorry, at a distance minus x, it's symmetric. So if the horizontal displacements of any point is equal to the horizontal displacement of its mirror image. Similarly, there is also symmetry about the x-axis, which means the vertical displacement So it is not just the horizontal, it's both the vertical. So horizontal and the vertical displacements are symmetric. And the same applies to y as well. Because we can see that if the forces and the structure is symmetric, the displacements are also symmetric. So this is one thing. What is the next thing we need to look at? So let us see. They are asking the shear forces at H and F are 0. Now let us see what is the expression for shear force at this point. So consider the member AD. So in the member AD, and this is the these are EF, GH. So this is bending in the vertical direction. So let us say V of minus X is equal to V of X. dV by dx of V of minus X is equal to dV by dx of, sorry, so d by dx, you can differentiate it on both sides, of V of minus X is equal to d by dx of V of X. So on the right hand side, what we have is just V dash of X. But on the left hand side, if you apply chain rule, you get a V dash of X multiplied by a minus sign. So you have V dash of minus X. There's another, the difference is with respect to X, so you have a minus sign. So what does this mean? If you take a point such that X is equal to X minus X, which point is that? If you take X equal to 0, which is along the y-axis, then minus V prime of 0 is equal to V prime of 0, which means the slope at that point, the slope at any point along the y-axis should be equal to 0. Similarly, you can do a similar analysis with the x-axis. You get u of y is equal to u of minus y. If you take the derivatives, you get u prime of y is equal to minus u prime of minus y. And substitute y equal to 0, we get u prime of 0 is equal to 0. So this means that, so here it is, dv by dx is equal to 0 everywhere along x equal to 0, and del u by del y is 0 everywhere along y equal to 0. Therefore, at the points E, F, G, and H, the slopes are 0. Do we have an option? Yes. So the slopes at the points E, F, G, and H are 0. The next thing to look at is the vertical displacements at H and F are 0. Is that true? No, that doesn't have to be true. So the points F and H, the vertical displacements are given by V of 0, but there's no condition on V of 0. We only have that V dash of 0 is equal to 0. So V of 0 can be anything. In fact, you can visually see that the deformed shape will be something like this. So option C is wrong. The horizontal displacements at H and F are 0. Now let us look at that. So the horizontal displacements, suppose U of X is equal to some value U naught, UH at the point H. Let us say the displacement of the structure at this point, at the point H, the horizontal displacement of the structure at the point H is given as UH, which is not equal to 0. Now consider a mirror image of a structure. you consider a mirror image, the loads and the geometry and the boundary conditions remain the same. So basically, a mirror image is to transform x to minus x. But then, if this is the case, then u of minus x becomes minus UH. But now we are looking at the point x equal to 0, which means u of 0 is equal to UH, but u of minus 0, which is also equal to u of 0, is equal to minus UH, which means UH is equal to minus UH. Therefore, UH has to be equal to 0. So the horizontal displacements of the points lying along a symmetry line has to be along a vertical symmetry line should be equal to 0. So option B is also correct. The horizontal displacements at H and F are 0. And the shear forces at H and F are 0. So at H and F, we have some V of X. We know the V of X is V of minus X. Differentiated 3 times. So first derivative, second, so this becomes 3 derivatives with respect to X. And here you get minus 1, the whole cube. 3 derivatives with respect to X evaluated at minus X. Now substitute X equal to 0, we get V of 0, triple derivative E, and multiply by EI. EI V triple derivative of 0 is equal to minus EI V 3 derivatives of 0. But this is nothing but the shear force. So the shear force at the point whenever X equal to 0, the shear force in the vertical direction should be equal to 0. So all along the y-axis, the shear force is 0. So option A is also correct. So the correct answer to this problem is A, B, and D. So to conclude, whenever we have symmetric conditions, the normal displacement, the displacement components normal to a plane of symmetry and the force components tangential to a plane of symmetry. Both are equal to 0. So this is a shortcut you can use for solving problems. Whenever you have symmetric structure, both the normal components to the plane of symmetry. So X and Y are planes of symmetry. The XZ plane and YZ planes are planes of symmetry. So the normal components of displacements, which are respectively the V along the x-axis and U along the y-axis, both of them are 0. And the tangential forces, so the shear force along X and Y, we are 0. Let's go to the next problem. So this is an interesting problem which appeared in GATE 2008. We have a statically indeterminate structure. So the beam GHI is supported by 3 pontoons as shown in the figure below. The horizontal cross-section area of each pontoon is 8 meters square and the flexural rigidity of the beam is 10,000 kilonewton meters square. The unit weight of water is given as 10 kilonewton per meter cube. For solving the problem, let us number these ends as A, B, C, and D. It's a paragraph link type question. So there are in the first part, we are asked to assume that the middle pontoon is removed. The support at H is removed. and we need to find out the deflection at the point H. The second part of the question, the support H is brought back, and we need to find the reaction at the point H. So this is an interesting question because these are not normal supports. They are not rigid the hinge supports. They, as the beam deforms, they also go down because water is uh, it's not rigid, so they also go down. But they don't go down fully. They don't go down freely without any resistance because of the buoyant force. So let us analyze the problem quickly. First thing, as usual, is to determine the degree of static indeterminacy. Let us solve this problem by the method of consistent deformation. So let us denote the pontoons by springs. Why am I denoting it by springs? Because we'll see very quickly that this be point A, B, C, D, G, H, I. So the degree we have the unknown forces AX, AY, GY, HY, and IY. So we have 5 unknown forces, 1, 2, 3, 4, 5, and also BY, 6 unknown forces. So the number of unknowns is 6. The number of equilibrium equations. We have 3, sigma fx0, sigma fy0, sigma mz is 0. But we also have 2 hinges. Therefore, we know that the moment at the point C and D in the structure is 0. So internal hinges we have 2. Therefore, the degree of static indeterminacy is 6 minus 3 minus 2, which is just 1. So this is a statically indeterminate problem of degree 1. Now we can eliminate a lot of unknowns such as AX, AY, and BY by just inspection. So if you look at the span AC, we know that all the forces are vertical, so AX is directly equal to 0. If you look at span AC, this is simply supported. And here you can only have a vertical shear force transmitted. There cannot be any moment. Therefore, AY should be equal to minus CY. But if you have two equal and opposite forces separated by some distance, then it will not be in equilibrium. And there is no moment allowed anywhere here. Therefore, if you take moments about the point A, we get CY is equal to 0, which also means AY is equal to 0. Similarly, we also have BY is equal to 0 and DY is equal to 0. So these two connections in this beam serve no purpose. So they can be directly deleted when we analyze the structure. So effectively, the useful part of the structure is only so much. Look at G, H, and I. And you have some forces acting here. The second thing is let us characterize the buoyant force. Suppose this pontoon, one of the pontoons that is considered, they are prismatic, they have a constant cross-sectional area. So let me draw the cylindrical part of it. It has a cross-sectional area A, and it is partially immersed in water. And let us say this is the equilibrium, whatever this at this level, it floats in equilibrium. And let us suppose it is pushed further by a distance delta. It is pushed further by a distance delta. We know that it displaces so much water. And by Archimedes' principle, we know that the buoyant force exerted uh, by the liquid on the immersed, partially immersed solid should be equal to the, let us call this as the buoyant force Fp. the upward buoyant force is equal to the weight of water displaced. Let gamma W be the unit weight of water. Delta is and the volume of water displaced is delta times A. We can see that this is a linear relationship if A is constant. Therefore, this gamma W times delta, we can take it as gamma W times A, we can take it as a spring constant K. That is why you can denote the buoyant forces by just like a spring. So it is something like K delta B. So this justifies denoting these as springs. Now let us solve the problem. So in the first case, we are asked to remove the pontoon at H. So this itself is a primary structure. We know that this is statically indeterminate to the first degree. By removing one redundant force at H, the structure you get is something like this. There is a concentrated force. Let the force be F. Now it is very simple to establish equilibrium of forces here. Let the forces in the springs be Rg and Ri. Again, you can use the idea of symmetry. So the total vertical force should be F, and the structure, boundary conditions, loading, everything is symmetric about this midpoint. Let this be L. This be L. Everything is symmetric about this dotted line. Therefore, Rg should be equal to Ri should be equal to F by 2. What is the bending moment diagram of this B? So the overhangs play no role because there is no forces, there is no loading in the span. So the bending moment diagram of this beam will be something like this. It's easy to find the maximum value occurs at the midspan. And how much is that? You know, it is PL by 4. So in this case, it is F into the span is 2L by 4. So it is FL by. Now, what is asked? We are asked to determine the displacement at H if there is no quantum. So the beam displaces something like this. It will not maintain these two, the points G and I will also go down. Therefore, if this is the initial configuration, the final configuration is something like this. It will not be like this. So the correct deformed configuration is this, and this is a wrong one. It cannot be like this because these 2 points have to go down. Let these displacements be delta G, delta I, and the middle one be delta H. To solve this problem, we can use the Castigliano's theorem. What does it say? So we have seen this in the last session. The displacement at the point of application of a force F. So if we want to determine the displacement at the point of application of a force F, it is given by the partial derivative of the complementary strain energy with respect to the force F itself. In this case, it is a beam. So the dominant component and it's a linear elastic solid. Therefore, the complementary strain energy is equal to the strain energy of the beam. So let us write the expression for the strain energy of the structure. So U has components from the beam, from the spring at H, sorry, the spring at G, and it also has component from the spring at I. So we know that the strain energy of the beam is given as M of X. So this is the internal force, the internal moment acting on the internal rotation, which is M by A, which is the curvature multiplied by dx. So this is the rotation. And the load is increased from 0, so you have a half. And this has to be integrated from, let us consider let us take the origin of the beam at this point, because it's So this integration runs from minus L by 2 to L by 2. So further, what is the strain energy in the spring at G? It is half K delta square. So half K delta G square plus half K delta I square. And we can get everything in terms of the forces. So delta G, you can substitute it as F by, so the force in the spring is F by 2 and the spring stiffness is K. So you can substitute this here. Therefore, you get F square by 4K. And this bending moment, it is easy to integrate. Again, we can see the integrand is an even function. It is the square of the bending moment. And the bending moment itself is linear. So the bending moment itself is linear. The m of x is given as, in this case, it is FL by 2 minus, so in x equal to n, the bending moment vanishes, and at x equal to 0, to have a maximum bending moment. This is how it is. And the square of this is an even function. It doesn't depend on the sign of x. Therefore, you can replace the integral from minus L by 2 to L by 2 as 0 to 2 times integral 0 to L by 2. F can be taken out. F by 2 can be taken out. So we have a 1 by 2 here. F squared by 4 L minus x the whole square divided by EI dx. This can be directly integrated. So we get we can take x squared by 4 commonly out. So we get L minus x the whole cube by 3 from 0 to L by 2 minus plus 1 by 3. So this transforms to f square by 4. This is nothing but L cube um, sorry, so this integral you need that is so we have complementary strain energy as integral from minus L by 2 to L by 2 1 by 2 EI FL minus fx by 2 the whole square dx plus f square by 4. Evaluate this integral. So this is not an even function in x. It is neither odd nor even. So, but if you do the transformation as some xi is equal to L minus x, therefore d xi becomes minus dx. And then, so the limits go from L by 2 to, so when x equal to minus L by 2, xi equal to, we can directly integrate this. So get f squared by 8 EI minus L by 2 to L by 2 L minus x the whole square dx plus f square by 4. So this is nothing but L minus x the whole cube by 3. There's a minus L by 2 to L by 2 x squared by 8 plus x squared by 4 cube. So when x equal to plus L by 2, we get L by 2, and when x equal to minus L by 2, we get 3L by 2. Therefore, the integral is cube. So this is 27 minus mm, 0. So this is all L minus L to L, minus L to L. Is minus L to L. So when L equal to 0, we have L minus x as L, and when L is equal to L, this term vanishes. Therefore, we get the expression for the complementary state energy as f squared by 24 pi plus f squared by 4. That's an L cube. Next set, LU star. This is the deflection effect, which means so these are all square terms. So f is retained. So this is the expression for the displacement at the point h. And if you substitute the values into it, we get delta h as 0.4 meters. So substitute k is equal to gamma w into a, where gamma w is 10 and a is 8 meters square. Substitute L is equal to 5 meters. So this is in the units of kilonewton per meter. L is 5 meters. EI is 10 power 4 kilonewton plus 5. Substitute all this, we get delta H is equal to 0.4 meters. For the second part of the question, it is said that the middle pontoon is brought back to its position as shown in the figure above. What is the reaction at H? So if the middle pontoon is brought back, then in addition to two forces that also has a spring stiffness K, the applied force is P. We can subsume this spring force onto the applied force P as this. So we can denote this as P minus K times delta H. So it's equal to a force P minus K times delta H. And we have displacements as well. But what is that we solve for? Here we can't enforce that the point. So what is the geometric compatibility condition? That is the tricky part of this question. You can see that there is no rigid support, therefore delta H cannot be 0. Delta G, delta I cannot be equal to 0. So what is the geometric compatibility condition? To see that, let us look at the uh, equilibrium of this. So the force in the spring is K times delta H. So the consistency condition is the downward displacement of the beam, delta H of the beam, should be equal to the displacement of the point H on the spring. On the spring, it is easy to compute what it is. It is a spring force, which is let the spring force be RH divided by the spring constant K. And what is the displacement of the beam at that point? So the displacement of the beam is we just found out here. It is FL cubed by 12 EA plus F by 2K. But what is F in this case? Now F is equal to P minus K, P minus RH. So K delta H is nothing but F is equal to P minus RH. So substitute everything into this. So we get 1 by L cube by 6CI plus 1 by 2K times P minus RH is equal to RH by K. Just rearrange. This is a constant. All the parameters are known on the left hand side on these. And here 1 by K is known. So just rearrange. We get P. We get RH as on rearrangement. We get 19.2 kilonewtons. You just substitute all your values. So that is an option. Option C. So that is the end of today's session. You can go through this. In case you have any doubts, you can read back. Yes, let me wait for a while, and if there are any doubts, I can take. I will end the session. It looks like there's no doubt. Let me stop the recording. Thanks.